All right, BJT circuits. First of all, they're simpler than MOSFET circuits for many reasons, mostly because the relationships between the input and the output are really, really simple. You can find output values from input values and vice versa. As long as you know the value of beta or alpha, you can basically translate. So things to remember, which we kind of have already gone over, the emitter current is just the collector current plus the base current. The collector current is related to the base current by beta and to the emitter current by alpha. The emitter current's related to the base current by beta plus 1, which means that the collector and emitter currents are only slightly different. They are different, but they're not really, really different. And then alpha you can find if you know beta by taking beta over beta plus 1, and if you know alpha, you can find beta by taking alpha over 1 minus alpha. Assume that RO is infinity unless you're told that it's not. In general, it's more often put into these circuits than it is to the others, but you will know whether if no mention is made of RO in the circuit, then you just leave it out. Otherwise, use it and it will generally be something rather large. So we're just going to look at circuit examples kind of slowly. And this first one has two voltage sources. It's kind of similar to one we did with MOSFETs, but we have VCC is 10 volts. We have two resistors, a base resistor and a collector resistor. And then we're going to assume VBE is 0.7 volts. Remember, VBE is just basically a forward bias PN junction, so generally the voltage will be, unless you're told to find it by iteration, which in all likelihood you will not be told to do that again. You probably had done with that. So, and beta in this case equals 50. So we want to find VBB so that VCE is 5 volts. One of the things that I will remind you of repeatedly, at this point in this particular example, the collector current goes through RC and the value of VCE would just be VCC minus ICRC. But if you have an emitter resistor, it's not that, because you're basically finding the collector voltage, but because the emitter is grounded, that's also VCE. So as we go on, you'll see sometimes VCE and VC are different because they should be if the emitter doesn't happen to be grounded. So all we do is use KVL. We use KVL repeatedly to analyze these. On the input side, which is basically called, the part to the left, we can take VBB minus IBRB minus VBE, and that will equal 0. And then on the output side, we'll have VCC minus ICRC minus VCE equals 0. But the input and output equations are linked together by beta, which they weren't in MOSFETs. They were completely separate, and you had to find whatever was at the input side, then find what's at the output side. And this time you don't kind of need to. So we can calculate IC really easily in this particular problem because we know what VCE is. So IC is just going to equal VCC minus VCE over RC, and we get 5 milliamps. So that is just simple Ohm's law and relatively easy to find. Once you get IC, you can find IB by just using the value of beta. IC over beta is going to be IB, so we take 5 milliamps over 50, we get 100 milliamps. Then, microamps, sorry. 0.1 milliamps. Yeah, I'm talking faster than you know how it is. Talking ahead of myself. Then we can use the KVL equation from the input side to find VBB. So VBB is IBRB plus VBE. We already know all those values, and we just plug them in, and we get 1.7 volts for VBE. VBB. Oops. I have like several examples with this same circuit. So that is a circuit that is in active mode. The next thing we want to look at is what would BBB look like, or be, if we put it right at the edge of saturation? Remember, in BJTs, the active mode is where we want to be, and saturation is when the collector current is at its maximum. And there's a kind of a boundary between the two, and I'll talk more about the boundary between the two next week when we talk about AC circuits. But at the very edge of saturation, VCE is about 0.3 volts. That's about right on the edge where it's still in the active mode, but it would just not take much at all to put it into saturation. So we call that the edge of saturation, which we didn't really have with MOSFETs, but we do with BJTs. So we still have the same value of beta, and we can use the output KVL equation to get IC again, but it's going to be different because now VCE is just 0.3 volts. So we go through and we calculate that. We get 9.7 milliamps, yes?
This is a theoretical question, but what's the purpose of finding values at the edge of saturation?
Because finding it right on the edge is more theoretical, but we find it in saturation, you see how different it is. So we might want to know what's the maximum current that's going to go through it in saturation. If you happen to be doing a switch, you'll be going between cutoff and saturation, so you need to know what the edge is. So it depends on the application. With an amplifier, you wouldn't really care, but with a switch, you would care because you'd be going from cutoff to saturation back and forth. So you'd want to know how much current the collector is going to have, which in this case is 9.7 milliamps, which is a lot more than the previous example. Then we can use the beta equation to find IB, and we get 194 microamps. And then we can go and solve for VBB in the same exact way we did before by taking RBIB or IBRB plus VBE. Sounds like something to eat. And you end up with 2.64 volts. So basically with the same circuit, you start out with 1.7, and as you crank up VBB, IC goes up and up and up, and it hits 9.7 milliamps right at the edge of saturation. So that's kind of the point of finding that. Then we can find VBB in saturation. In saturation, the beta value actually doesn't apply, because when it gets pushed into saturation, the base current can continue to go up, but the collector current can't, so the beta value is different. Oftentimes you calculate that, but this is just going to tell you that the forced beta in that case is 10, since we can't really measure anything else. Do the same process. We find the current's 9.8 milliamps. It didn't go up very much. Just a little bit, but that's the most current you're going to get out of it. That's not going to change. The beta equation gives IB of 980 microamps, which is a lot more than the last time. So the base current went up a lot, but the collector current didn't go up much because beta is dropping to make up for that. And then we can find VBB, and it's 10.5 volts. So it went way up, and basically the more you turn it up, the base current will keep going up, but the collector current will not.
So for, you said that IC keeps going up and IB?
No, IB keeps going up. IC does not. It just levels out when you get to saturation. It just stays. It pretty much can't go up anymore because VCE is stuck at 0.2 volts. So basically, it's going to be, by Ohm's law, stuck at one value. But the base current can keep going up, and as it does, the beta value, which relates them, has to go down to adjust for all of that. All that being said, this particular bias circuit is a terrible bias circuit if you actually wanted to use it for anything. Because part of the reason is you have to have a heavy dependence on beta in this particular circuit, because as it changes, it directly changes a lot. And if you design a circuit like this, first of all, you have two power supplies, which is a real pain. And the other problem is that if you have your transistor blow up and you go and get another transistor and put it in, and it has a different value of beta, the whole circuit will not work the same way. And so basically, better bias circuits work by not depending so heavily on beta. And we're actually going to cover the most popular bias circuits next time. One thing I do have to say about NPN versus PNP, I feel totally comfortable assigning problems with either because they're exactly the same. It's just that PNP values are backwards. It's not the same with a PMOS where you have to remember whether you use the absolute value of something or not. So I feel completely confident that if I give you a PNP problem, you won't have any problem with it because everything just goes the other way. So don't expect that I won't ever give you one of those, whereas I don't tend to give PMOS problems, but I do tend to give PNP problems from time to time. So to figure out whether a transistor is in active mode or saturation mode, because this is an important question, basically with any circuit that you have, you want to know if it's in cutoff or if it's conducting. And usually it's pretty easy to tell if it's in cutoff based on the circuit. Nothing would be happening. So if it's conducting, then we want to know if it's in active or saturation mode. And we usually don't know by just looking at the circuit. I never know. So you assume it's in active mode to start out with. Then you check after you find your values to see if the actual values are consistent with active mode. You can go and check if VCB is greater than negative 0.4 volts. That's one way to check. Another way is to just blaze ahead, get all the values, and then see if something really doesn't make sense. And what usually happens is, depending on how you analyze the circuit, you're going to find that at some point you get a value that just absolutely can't exist in that circuit. For instance, if you have a VCC of 15 volts and you go ahead and you find a base current and that's all good, and you find your collector current and that's all good, and then you try to find, say, the voltage at the collector, you take VCC and you subtract IC/RC, and you get a negative number, which won't happen in a circuit where you have positive 15 and 0. Or you try to find VCE, and VCE is 10 times bigger than your DC voltage source, things like that. That is what ends up happening if it's not in active mode. So you get your values in active mode, and then as you're getting the rest of the node voltages and current, you find out they just absolutely don't make sense. So if those two conditions are true, I can never remember to look for that. I just blaze through and then suddenly come up with something like, oh, this is 75 volts. That can't be. Okay, I guess it's in saturation. So that's how I've always done it. But if those aren't true, if you either don't come up with VCB greater than negative 0.4, or you have values that just don't work in the circuit, then you assume that you're in saturation, and you use the saturation model, which basically means you set VCE to 0.2 volts. So if a problem asks you to look for VCE and it ends up being in saturation, just set that to 0.2 and then go find the collector current and the base current separately, because then you don't know what beta is. Once it's in saturation, you will not know. So once you get through kind of analyzing it, you check and see if it works, and then whatever beta is for that problem, it won't be the same as the beta that was given. All right, so bias mode, basically when we want to have a circuit that will operate as a bias circuit. This is a little more realistic, what you might encounter. We have two voltage sources and two resistors. You notice there is an emitter resistor and there is a collector resistor, and the collector emitter voltage is actually the DC voltage that is present at the output when you're sending an AC signal through. Oftentimes it's half-ish of the collector voltage, like VCC. That's a good design if you can make it half that. Sometimes it comes out to that, sometimes it doesn't. But that's kind of the best you can get. You will get pretty much the same KVL equations, but this is just slightly different. Now this is easier because there's no base resistor. But you notice we have a VBB, and VBB minus VBE minus IBRE equals 0. This is not the same equation that we got last time. It's not the same equation that we'll probably get next time. So you can't go through and memorize these because it doesn't work. They're not ever the same. So you have to actually use KVL the way you know how to use it to figure out what the input equation is. And this time all we have is VBB and VBE between the base and emitter, and then IERE going around that bottom loop. On the output side, we have, again, something different than last time, but KVL consistent, that if we start with VZC, subtract ICRC, then subtract VCE, then IERE, we get 0. So that, again, is different. So you actually have to look at the circuit and do the actual voltage drops to get the right equation. The input equation only has one unknown because we know VBB and VBE. So we can actually solve for IE first this time. Sometimes it will be IC, sometimes it will be IB, but always find the easiest thing first. And the easiest thing to get out of here is IE to begin with, and when we do that, we get 1 milliamp for IE. Then we know the value of beta, and we can either you can find alpha, or you can actually just use beta over beta plus 1, but I think this time I found alpha. So if you want to find IC, we just find alpha. Alpha is just beta over beta plus 1, so we get 0.99. Alpha is going to be 1 or less. If you ever calculate alpha and it's greater than 1, you've done something wrong, because it's definitely going to be 1 or less. And it's usually going to be significantly less than 1, not 0.99, but in this case it's 0.99. So that means that IC is going to be 0.99 milliamps. And then base current, we can get a couple ways. We can use beta, or we can just take IE minus IC, and either way you're going to end up getting 10 microamps. Be careful when you're doing these problems and don't round values too much, because if you round IE and IC too much, then you'll end up losing the base current completely. They will be close. As you can see in this, we've got 1 milliamp and 0.99 milliamps, but don't round that 0.99 to 1, because then you've lost the critical part of the circuit. So this is one of those cases where you want to kind of be careful. Don't round too much, because you will lose the values that you need. So once we've found the 3 currents that go in there, we can actually put them into the circuit, and you see that 0.99 milliamps and 10 microamps add up to 1 milliamp, which they should. So the collector and base currents are going to add together to give you the emitter current. And then we can find the node voltages for the collector and the emitter. Those are the only 2 nodes that we don't know. We can find VC by taking VCC minus ICRC. And that gives us the collector voltage, not the collector emitter voltage, but just the voltage at that node. So if we take 10 minus 0.99 milliamps times 4.7 K, we get 5.3 volts for VC. And then VE, we can actually find 2 different ways. We could take 1 milliamp times 3.3 K, and that would give us 3.3 volts. Or we can take VBB minus VBE and also get 3.3 volts. So more than one way to do it, but you should get the same value. So then there's a 2 volt drop between the collector and the emitter. So VCE is greater than 0.3 volts, so the transistor's in active mode. That's another way you can check. There's a lot of ways you can check. But if VCE comes out not a weird number, but generally a positive number in an NPN that is between, there's a reasonable range value, not 0.3, but generally a number that is, some fraction of the collector voltage, then that's going to end up probably being the best assumption that you can make. So this is not, again, terribly difficult. This is pretty much only going to be like circuit analysis that you're doing, even more so than with MOSFETs. With MOSFETs, you had to solve the quadratic and all that and figure out which value of drain current. You don't even have to do that with BJTs. All you have to do is solve the circuit with the values that are given. And in fact, during the first or second week of class, I can't remember which one, I think you had a participation problem that was basically a BJT, except there were voltage drops instead of, I can't remember exactly how it was put together, but it was basically an amplifier circuit, except it didn't show the transistor. It just had proper voltage drops instead. So, PNP values. A PNP circuit sometimes is going to look like this with two voltage sources, a plus and a minus. It can also be done with a ground and a positive voltage. That are done like that more often. But right now, since we have a collector resistor and an emitter resistor, I did it right. I always get upside down with these. But notice the emitter is on top and the collector is on bottom, because generally the PNPs are flipped over and the emitter is actually coming in from the top instead of from the bottom. So we want to find the easiest thing first. And the easiest thing to find is VE, because it's 0.7 volts above the base. So we know VBE is 0.7 volts, or VEB in this case, so we know that VE is 0.7. So we can instantly kind of get VB and VE just by looking at the circuit. Don't have to calculate anything, you just write them down, because you already know those. So that's 2 out of 3 of the node voltages already. We can find IE really easily because we know the voltage at the top of RE, we know the voltage at the bottom of RE, and we know the value of RE. So we can find IE just using Ohm's law. Then we can use the alpha/beta relationship, because beta is given, and that's frequently the way it is given as put next to the transistor in the circuit, and that is frequently a way that the value of beta is passed on to whoever is analyzing it, if there's room on the page. So we can just find IC using alpha IE. Alpha is equal to beta over beta plus 1, so I think I didn't even calculate it separately. I just came up with a value. Your IC should always be less than IE, obviously, which it is, just slightly. And then we can find IB either by taking IE minus IC. I think this time I took IC over beta and got the value that way. That's going to give you a more accurate result, because you'll notice if I took IE minus IC, I'd actually get 50 microamps, and it's really 46. So using beta is generally a better way of doing it. And then I can find the last value of the last node value by taking VC, which is what I want, and that's going to equal -10 plus ICRC. So you're starting at the bottom and going up to get to that node. So we take -10 plus ICRC, plug them in, and we get -5.4 volts. Well, that's easy. Now, if I find if I put in a base resistor, this changes it slightly, because before, the base current, we found it, but it really didn't matter. The base voltage was 0 and the emitter voltage was 0.7 because the base was grounded. But if we have a circuit in which there is a resistor, then the base is not connected to ground. So then we have to start writing out equations and figuring out a way to solve for just one unknown. And this is why sometimes transistor circuits are difficult, because you actually do have to look at it and figure out what do you know, what do you not know. Start out by writing out KVL equations, and on the input side would be starting at ground and just going through the 10K ohm resistor and then through VBE and then the 1K and then the 5. So we kind of go there. We start and say we have IBRB, then we add VBE, then we add IERE to get to the 5 volts that was applied. Then you notice we have two unknowns in that equation. We have IB and we have IE. We know all the other values. But IE is equal to beta plus 1 IB. So generally what is done is we just substitute that into the original equation, and now all we have is IB. And this is what you can notice from this. We have two values, and we have IB here and ID here. If we were using Ohm's law, we would take IB up here, we have IERE up here, and that gives us a voltage. Down at the bottom, we have IB, and then we have this whole quantity, beta plus 1 RE. What's happening mathematically is that the value of RE is being increased by beta plus 1 to accommodate for the smaller current. So we actually think of beta plus 1 RE as a resistance in and of itself. So beta plus 1 has no units, so if we multiply RE times beta plus 1, we can just get a bigger resistance to adjust for the fact that the current is smaller. Now that we have the equation set up, we're just going to go through and solve for the three currents. So IB, we're just going to take the total voltage across IB, which is just going to be 5 minus VBE, and we're going to divide by the total resistance, which is RB plus beta plus 1 RE. And when we do that, we get 104.88 microamps. Once we've done that, finding IC and IE is really easy because we're just going to multiply each one of them by beta or beta plus 1. So IC we get as 3.146 milliamps, and IE we get as 32.251 milliamps. So now what we're going to do is we've got the currents and we've assumed the transistors in active mode. So now what we're going to do is just test and find the node voltages. And if the node voltages don't work, then we know the transistor's not in active mode. So we can get a value for VB, just taking IB times RB. And when we do that, we get 1.049 volts. And that's not particularly helpful because that could or could not be a valid value. For VC, we have minus 5 plus ICRC, and that is definitely a problem. We're going to go on and find VE just for grins. And when we do that, we get 1.749, but the 26.46 volts is not going to work. The other two would work, but we can't have 26 volts in a circuit that goes from plus 5 volts to minus 5 volts. So that's not possible, which means the transistor is in saturation. So we're going to have to go back and reanalyze the circuit using different values. I don't know what beta is, so we can't have value of beta there, but I do know what VEC is because it's in saturation. So we set that to 0.2 volts, and we don't know what beta is. So now we can't use that to actually come up with a value. But what this means is the value of VE is going to be VB plus 0.7. That all works. And VC is going to be VE minus VCE saturation, which we know what that is. So that's going to be like VB plus 0.5. So we have two ways to find values based on VB. And we can use that to go into each current and have a relationship between the current and the base voltage. So all three currents, you'll notice, when you start plugging in the value of it related to the base voltage, we actually end up with like one unknown because IE equals IC plus IB. So we can make that into one long equation where we just solve for VB. And that's what, so it ends up being a completely different type of analysis when it's in saturation, which again is sometimes what stumps people. Is you have to go back to the beginning, you have to have different assumptions, but you have different things that you know, but you can still solve for the values that you need to. So now that I have IE, IC, and IB all in terms of the base voltage, I can take that and just make one big long equation with just IB or VB in it. And when we go through and find that, we can solve for VB. That's 3.13 volts. And then we already had the relationships for VE and VC, and you'll notice that they are actually 0.2 volts apart, which is good. So we have those values. We have the relationships from the previous page, which told you what the currents were. So we can go and find each one of those currents. You'll notice that the base current is rather large. It's much larger than it would be in an active mode circuit. And you also notice that IE and IC are very, very different from each other. And this is because beta is a different value. The way we would find beta in this circuit, it would just take IC over IB. And if we do that, we end up with 2.76 for the value of beta. So this is why the collector current and the emitter current are very different. They're still related by beta over beta plus 1, but beta is so small that it makes a radical difference.